Okay, back when we were talking about what is light and the debate over light as a particle, light as a wave, I had told you that there were two experiments that were done that could only be explained if light was thought of as a particle. One was the photoelectric effect. It's time to talk about the second one, the Compton effect. Now, you'll probably be happy to know that the Compton effect is much simpler than the photoelectric effect. Okay, so the Compton effect is named after Sir Arthur Compton. So he was British, and the Sir means he was knighted. Okay, and what he did was he took high energy radiation, X-rays. And when you have high energy radiation, that means you get photons that have high energy, right? So high energy means high frequency, which means short wavelength. So imagine that we have high energy radiation coming in, and he is striking these high energy radiation. This high energy radiation is striking a surface, okay? And in striking a surface, it ends up hitting electrons, and what happens as a result is that the electrons are ejected. Now, this might sound a lot like the photoelectric effect, except in the photoelectric effect, the radiation is completely absorbed. But in the Compton effect, the electron is ejected and then a lower energy, longer wavelength photon is given off. Okay, so this is a high energy photon, E equals EP, remember, equals HF. So it's high energy, it's high frequency, short wavelength, but then the new one that's given off, they're scattered. These are called the scattered photons, have a much lower energy. Okay, so it's a different EP, it equals a different HF, and it's a much tinier HF. Okay, now when Arthur Compton looked at this, it was like, okay, wait, something's wrong here, because this electron was just sitting here, didn't actually have like momentum or kinetic energy before the collision, and now it goes off with both kinetic energy and momentum. It means that this collision wouldn't be elastic, that it was breaking the laws of physics, that momentum was not conserved. And scientists just were not ready to accept the fact that momentum couldn't have been conserved. But if we think of photons as particles of light, then we can say, okay, it makes more sense that there is an elastic collision. Okay, so if you want to write some notes here. So you have high energy, high frequency radiation striking a surface. So high energy, high frequency radiation or striking a surface. So these are the photons, right? Striking a surface. Electrons are ejected, and the leftover energy is scattered or released as lower frequency, lower energy photons. So these are high frequency, high energy photons. They strike a surface. Electrons are ejected, and then you get scattered lower energy, lower frequency photons, okay? These are released or scattered. When we look at the kinetic energy and momentum of the photons and the electrons, we realize that they are both conserved and that the collision is elastic. But what should be causing you an issue is that photons then must have momentum. And we know from grade 11 physics that momentum is equal to mass times velocity. The problem is that photons don't have mass. Anything that's traveling at the speed of light cannot have a mass. Photons are particles of light. So that means they're traveling at the speed of light. They always travel at the speed of light. Therefore, they never have mass. So how the heck do they have momentum? Okay, so what we say is they have no rest mass because they're never actually at rest. But they do have energy and they do have momentum. So we know our equation for energy is EP is equal to HF. So what happens then is we define the momentum of a photon. We define it. So we didn't figure it out. We defined it. We set it based on all the experiments. So we set the momentum of a photon, P, to equal the energy divided by the speed of light. Okay? Now, energy, we know, is just HF. And we know the speed of light is really just F lambda. So the F's will actually cancel here, and the momentum of a photon is H over lambda. This is the most common equation. You will sometimes see E over C, but it's usually H over lambda. Okay, if we think about the units, joules seconds over meters. A joule is a Newton meter, so a Newton meter second over a meter. Meters cancel, so we're left with Newton seconds. A Newton is a kilogram meter per second squared times a second, and so we're left with kilogram meters per second, which is what momentum is measured in. Mass times velocity, kilogram meters per second. Okay? So looking at this equation, what it tells us is the momentum of the photon is only dependent on its wavelength and therefore on its frequency. The H doesn't change, the C doesn't change, so it's the frequency or the wavelength that will determine the momentum of a photon. Okay, so this is the Compton effect. We'll talk about its significance a little more in person, but I just wanted to give you a bit of an intro to it. So to recap again, you take high frequency, high energy photons, and he used X-rays. Okay, shot it at a surface where of course there were electrons. Electrons got ejected, just like they did in the photoelectric effect, but this time the leftover energy wasn't absorbed, it was scattered as lower energy, lower frequency photons. And so what this led us to was to try to make sure that the conservation of momentum held. And in order for the conservation of momentum to hold, we needed to think of light as a particle, and we needed to then to figure out what the heck could this momentum of the photons be when we knew the photons didn't have light. And so coming from all of this is that we get an equation that where we can calculate the momentum of a photon if we know its wavelength, or of course if we know its frequency, because if we know its wavelength or its frequency, we can find its wavelength because we know C is equal to F lambda. Okay, so this is the equation to calculate the momentum of the photon. There is one question on page 571. It is question number 13, I think. Yeah, that asks you to calculate the frequency of this photon. So perhaps you could do this now. So number 13 on page 571. And I will give you other homework aside from that. Okay?